in the video lecture series related to heat and mass transfer. We are dealing with convection chapter. In this lecture, we are going to learn how to solve the problems related to the natural convection and mixed convection, that is nothing but combination of free convection and forced convection. So first of all, to solve the problems related to the natural convection, we should know some formulas, some basics related to the natural convection. So it has been observed that the transition in free convection boundary layer occurs when the value of Reynold number approaches to 10 raised to 9. Transition in the boundary layer, that is nothing but transition from laminar flow to the turbulent flow. So it will happen at a 10 raised to 9 Reynold number. So Reynold number is nothing but multiplication of Grashoff's number and Prandtl number. Multiplication of Grashoff's number and Prandtl number. Here this Grashoff's number only dealing with the convection. So in case of a natural convection, we should consider that the 10 raised to 9, below 10 raised to 9 Reynold number, there should be a laminar boundary layer, and above 10 raised to 9 there should be a turbulent boundary layer in a rough manner. Okay, so dimensionless number, we have seen these dimensionless numbers are derived by using the dimensional analysis applied to the natural convection. So in that case we get the Nusselt number. Nusselt number is equal to H multiplied by L divided by K, where H is heat transfer coefficient, L is the characteristic dimension of the geometry, divided by K is the thermal conductivity. Then we know the Grashoff's number denoted by capital G small r is equal to L cube multiplied by beta multiplied by G multiplied by delta t divided by nu cube, a nu square. So L cube, L is nothing but characteristic dimension of the geometry, beta is the volumetric expansion of the fluid, G is the acceleration due to gravity, and delta T is the temperature difference between the surface and the fluid, or fluid and surface, whichever the more. So Prandtl number PR is given as mu Cp divided by K, where this mu is the dynamic viscosity, Cp is the specific heat, and K is the thermal conductivity. Here nu is the kinematic viscosity. In Grashoff's number, nu is the kinematic viscosity. So we have to derive some empirical correlations to solve the problems related to the natural convection. Actually, we know that Nusselt number is the function of a Grashoff's number and Prandtl number, and one new form of a dimensionless number we have introduced in the natural convection, that is nothing but Grashoff's number multiplied by Prandtl number. It is called as a Reynold number. So in a general format, Nusselt number can be interpreted as Nusselt number is equal to C multiplied by GR raised to M multiplied by GR raised to A multiplied by PR raised to B. So where C, A and B are the constants. So and if you form this equation, so Nusselt number for a vertical plate and cylinder, it will be given as a Nusselt number, average Nusselt number is equal to 0.59 into bracket GR multiplied by PR raised to 1 by 4. So this will be applicable for the laminar flow only, laminar flow over the vertical plates or vertical cylinders. So laminar flow will be considered when the Grashoff's number multiplied by Prandtl number value is greater than 10 raised to 4 and less than 10 raised to 9. So in that case we can use this equation. When this particular product of Grashoff's number and Prandtl number is greater than 10 raised to 9 and less than 10 raised to 12, in case of a vertical plate and a cylinder, then we have to use the another correlation, that is nothing but average Nusselt number is equal to 0.10 into bracket Grashoff's number multiplied by Prandtl number raised to 1 by 3. So this is nothing but what? The turbulent flow. This equation should be used for the turbulent flow. Then the Churchill and Chu correlation is also we can use for vertical plates and cylinders. So according to this Churchill, the flow will be laminar when the Grashoff's number and Prandtl number product is less than 10⁻⁹. So in that case, the Churchill has given the average Nusselt number is equal to 0.68 plus 0.67 multiplied by Grashoff's into bracket Grashoff's number multiplied by Prandtl number raised to 1/4 divided by in a square bracket 1 plus in a bracket 0.492 divided by Prandtl number bracket complete raised to 9/16 square bracket complete raised to 4/9. Okay, so this particular equation, Churchill and Chu equation, we can use if Grashoff's number multiplied by Prandtl number product is less than 10⁻⁹. Okay, then next Churchill has given another equation for the turbulent flow, that is nothing but if the Grashoff's number and Prandtl number product is greater than 10⁻⁹. So Churchill has given Nusselt number, average Nusselt number is equal to in a square bracket 0.825 plus in the numerator 0.387 in a bracket gr multiplied by pr raised to 1/6, where this gr is the Grashoff's number, pr is the Prandtl number, whole divided by in a square bracket 1 plus in a bracket 0.492 divided by Prandtl number bracket complete raised to 9/16 square bracket complete raised to 8/27 complete square bracket raised to square. Okay, so these two equations are provided by Churchill and Chu for the vertical plates and the vertical cylinders. So then horizontal plates, if the geometry is horizontal plate, then there are two cases. The first case is upper surface heated or a lower surface cooled. Okay, so if this is the condition, the upper surface heated or a lower surface cooled, so in that case the laminar flow for the horizontal plates should be considered if the product of Grashoff's number and Prandtl number is greater than 10⁵ and less than or equal to 2 into 10⁷. So in this condition for the horizontal plate, the average Nusselt number can be written as average Nusselt number is equal to 0.54 into bracket Grashoff's number multiplied by Prandtl number raised to 1/4. If this product is greater than 2 into 10⁷ and less than or equal to 3 into 10⁻⁻, then that flow will be considered as a turbulent flow. Okay, then the Nusselt number, average Nusselt number can be written as 0.14 into bracket gr multiplied by pr raised to 1/3. Okay, if you observe the equations from the starting point, there will be only two changes in the equation, that is nothing but here the multiplication factor whatever is there and raised to factor. So these two factors are changing in every correlation, so it will be easy to remember the things. So here also you can see that the multiplication factor and raised to factor, so these two we have to remember. Okay, the basic correlation is Nusselt number is function of Grashoff's number and Prandtl number. So this is the first case in case of a vertical plate. In case of a horizontal plate, that is nothing but the upper surface heated or a lower surface cooled. Now the second case is the lower surface heated or upper surface is cooled. So in that case, the laminar flow will be considered if the product of Grashoff's number and Prandtl number is greater than 3 into 10⁵ and less than or equal to 3 into 10⁻⁻. So in that case, the average Nusselt number can be written as average Nusselt number is equal to 0.27 into bracket Grashoff's number multiplied by Prandtl number raised to 1/4. And turbulent flow will be considered as when Grashoff's number and Prandtl number product is greater than 7 into 10⁶ and less than or equal to 11 into 10⁻⁻. So in that case, the Nusselt number can be written as average Nusselt number is equal to 0.107 into bracket Grashoff's number multiplied by Prandtl number raised to 1/3. Now the third geometry is horizontal cylinder. Vertical cylinder, for the vertical cylinder and vertical plate, the equations are same. Now next we have to consider the horizontal cylinder. For the horizontal cylinders, the laminar equation is given by laminar and turbulent equations are given by the Adams correlations. Okay, so Adams has given these two correlations for the laminar flow and turbulent flow. So according to Adams, laminar flow in case of a horizontal cylinder should be considered when the Grashoff's number and Prandtl number is in between 10 raised to 4 and 10 raised to 9. So in that case, the average nozzle number can be written as 0.53 into bracket Grashoff's number multiplied by Prandtl number raised to 1 by 4. And the turbulent flow will be there if the product of Grashoff's number and Prandtl number is greater than 10 raised to 9 and less than 10 raised to 12. So in that case, the correlation will be average nozzle number is equal to 0.13 into bracket Grashoff's number multiplied by Prandtl number raised to 1 by 3. Now the Churchill and Chu correlation is one kind of relation, we can say that, whose range is very much wider. So that is nothing but this equation, Churchill and Chu equation, can be applicable for the product of Grashoff's number and Prandtl number in between 10 raised to minus 5 to 10 raised to 12. So if the Grashoff's number and Prandtl number is greater than 10 raised to minus 5 and less than 10 raised to 12, then we can use the Churchill and Chu correlation also. So nozzle number, average nozzle number has been given by Churchill and Chu correlation. The average nozzle number is equal to, in a square bracket, 0.60 plus 0.387 multiplied by Grashoff's number multiplied by Prandtl number raised to 1 by 6 divided by, in a curly bracket, 1 plus, in a bracket, 0.559 divided by Prandtl number, bracket complete, 9 raised to 16, 9 divided by 16, in a curly bracket complete, raised to 8 divided by 27. So this equation we can apply for the product of Grashoff's number and Prandtl number greater than 10 raised to minus 5 and less than 10 raised to 12. So for all this particular correlation, the fluid properties, we should take the fluid properties at a mean film temperature. So that is nothing but what? The average temperature of surface and the fluid. So the mean film temperature can be given as T suffix mf is equal to T suffix s plus T naught divided by 2. So here this T suffix s is the surface temperature and T naught is the fluid temperature. So in case of horizontal cylinder, outside diameter is used as a characteristic dimension. Okay, so diameter of the cylinder will be considered as a characteristic dimension in case of a horizontal cylinder, whereas in case of a vertical plate, horizontal plate and vertical cylinder, its length should be used as a characteristic dimension. Its length should be used as a characteristic dimension in case of a vertical plate, horizontal plate and vertical cylinder. In case of a irregular plate, the characteristic length is defined as the surface area divided by the perimeter of the plate. In case of irregular surface of the plate, we have to consider the characteristic length of the plate is equal to surface area divided by the perimeter of the plate. So here we go, the first problem related to the natural convection or free convection. So statement is, a vertical cylinder 1.5 meter high and 180 mm in diameter is maintained at 100 degrees Celsius in an atmosphere environment of 20 degrees Celsius. Calculate heat loss by free convection from the surface of the cylinder. Assume properties of air at a mean temperature as density, that is rho is equal to 1.06 kg per meter cube, nu, that is kinematic viscosity, is equal to 18.97 into 10 raised to minus 6 meter square per second, specific heat, that is Cp, is equal to 1.004 kilojoule per kg degree Celsius, and and the thermal conductivity K is equal to 0.1042 kilojoule per meter hour degree Celsius. Okay, so here the thermal conductivity is given in a kilojoule per meter hour degree Celsius. So we have to do the conversion of this thermal conductivity into watt per meter degree Celsius for the simplicity of calculation. These are the properties of air. It is mentioned in the problem itself, so we need not to go for the property table. Now here we can say that the given data is length of the cylinder is provided as 1.5 meter, diameter of the cylinder is provided as 180 mm is equal to 0.18 meter. So surface temperature of the cylinder is 100 degrees Celsius and the fluid temperature which is flowing over the cylinder is 20 degrees Celsius. The fluid properties, that is nothing but air properties, are provided as Cp 1.004 kilojoule per kg degree Celsius, density 1.06 kg per meter cube, thermal conductivity K is equal to 0.1042 kilojoule per meter hour degree Celsius, kinematic viscosity nu is equal to 18.97 into 10 raised to minus 6 meter square per second. And here we have to find the heat loss by free convection. Here we have to find the heat loss by free convection, that is nothing but Q we have to find out. So at the start only in the solution, first of all we have to calculate the mean film temperature. So mean film temperature is nothing but TMF or TFM, mean fluid temperature, is equal to surface temperature plus fluid temperature divided by 2. Now here in the given data, the surface temperature is 100 degrees Celsius and the fluid temperature or air temperature is 20 degrees Celsius. So we have to add this and we have to divide by 2. So here we have done that particular addition and divided by 2. So mean film temperature is equal to 100 plus 20 divided by 2 is equal to 60. So we'll get the mean film temperature and whatever the properties are provided, so that properties are provided at a mean film temperature only. So we need not go for the property table. Now on the basis of a mean film temperature we can determine the coefficient of volumetric expansion. So coefficient of volumetric expansion, that is nothing but beta, can be written as beta is equal to 1 divided by mean film temperature plus 273. That is nothing but what? The mean film temperature we have to convert into a Kelvin. Okay, and we have to take the reciprocal of that so that it will be a volumetric expansion. Its unit will be Kelvin raised to minus 1. Now here we have done that the coefficient of volumetric expansion is equal to 1 divided by 60 is our mean film temperature plus 273, that is we have converted that mean film temperature into a Kelvin. So it will becomes a 0.003 Kelvin raised to minus 1, Kelvin raised to minus 1. Then we have to determine the Grashoff's number, which will be useful for our correlation. So Grashoff's number value we can determine by using the formula. So Grashoff's number is equal to characteristic dimension raised to cube, that is nothing but L cube multiplied by G multiplied by beta multiplied by delta T divided by nu square, where L is the characteristic dimension. Okay, so in case of cylinder, here we have to remember that the cylinder is vertical, a vertical cylinder is provided. So in case of a vertical cylinder, the length of the cylinder should be considered as a characteristic dimension. In case of a vertical cylinder, the length of the tube should be considered as a characteristic dimension. Here the same thing we have to determine. So L cube multiplied by G multiplied by beta multiplied by delta T divided by nu square. So L is the characteristic dimension. In case of a vertical cylinder, we have to select the length of cylinder as a characteristic dimension. So 1.5 meter is the tube length. 1.5 meter is the tube length or the cylinder length. So we have to select this 1.5 meter as a characteristic dimension. So 1.5 raised to 3 multiplied by 9.81 multiplied by beta value is 0.003 multiplied by delta T. Delta T is the temperature difference between the surface and surrounding. So here the surface temperature is 100 and the surrounding temperature is 20. So 100 minus 20 divided by nu square. So from the properties of the air we can get the kinematic viscosity value, that is nu. So we have to take the square of that nu value. So nu value is 18.97 into 10 raised to minus 6 and its square should be done. Okay, so we'll get the Grashoff's number value as 2.208 into 10 raised to 8. Now we have to determine the Prandtl number. So Prandtl number can be written as, or its equation we can write as PR, that is Prandtl number is equal to mu Cp divided by K. So mu is the dynamic viscosity, Cp is the specific heat, and K is the thermal conductivity of the air. Now here in this case, mu value, that is dynamic viscosity value, is not given directly. So we have to derive that value. So mu is nothing but dynamic viscosity multiplied by kinematic viscosity. Dynamic viscosity multiplied by kinematic viscosity is nothing but this. We can say that the density multiplied by kinematic viscosity is nothing but dynamic viscosity. So the density is given as 1.06 kg per meter cube, and the kinematic viscosity is given as 18.97 into 10 raised to minus 6 meter square per second. So that we can say that the dynamic viscosity we will get as 20.1082 into 10 raised to minus 6 kg per meter second. Okay. Now next, the thermal conductivity we have to convert in a required format. So thermal conductivity is given as 0.1042 kilojoule per meter hour degree Celsius. So first of all we have to convert kilojoule into joule. So for that purpose we have to multiply with 10 raised to 3, and we have to convert hour into second. So we should divide it by 3600. So it will be converted as a joule meter second, joule per meter per second per degree Celsius. So joule per second is nothing but watt. So after doing the calculation we will get the K, that is thermal conductivity value, as 0.02894 watt per meter degree Celsius. So thermal conductivity value we get here, and mu value also we will get, and Cp value is provided as a given quantity in the problem, in the properties of air. So Prandtl number is equal to 20.1082 multiplied by 10 raised to minus 6 is the dynamic viscosity value, multiplied by 1.004 is the Cp value in kilojoule per kg Kelvin. So kilojoule will be converted into a joule value. So for that purpose we have to multiply with 10 raised to 3 or 1000. So here we have multiplied with 1000 divided by thermal conductivity value as 0.02894. So that we will get the Prandtl number is equal to 0.6976. Next thing is nothing but we have to determine the type of the flow, whether the flow is laminar or whether the flow is turbulent. So for that purpose we have to find out the Rayleigh number, or the product of Grashoff's number and the Prandtl number. So Grashoff's number is 2.208 multiplied by 10 raised to 10 multiplied by 0.6976, that is the Prandtl number. So we'll get the value 1.54 into 10 raised to 10. So this value is greater than 10 raised to 9 and less than 10 raised to 12. So we can say that the type of the flow is turbulent flow, or the value is in the turbulent range. So we can use the equation for vertical cylinder for a turbulent flow. So this equation is average Nusselt number is equal to 0.10 into bracket Grashoff number multiplied by Prandtl number raised to 1 by 3. So the average Nusselt number equal to, we have to put up the values of Grashoff's number multiplied by Prandtl number. So we have determined this product over here. Just put up this value in this particular bracket. So it will be 0.10 into bracket 1.54 multiplied by 10 raised to 10 raised to 1 by 3. So Nusselt number, average Nusselt number we will get as 248.79. So on that basis we have to find out the average heat transfer coefficient. So we know that the Nusselt number formula, average nozzle number is equal to average heat transfer coefficient multiplied by characteristic dimension divided by thermal conductivity. So on that basis we can determine the average heat transfer coefficient value, as we know the average nozzle number value, characteristic dimension value, and the thermal conductivity value. So we can determine H bar is equal to average nozzle number multiplied by thermal conductivity divided by characteristic dimension. So H bar is equal to 248.79, that is the value for the average nozzle number we have determined on the basis of correlation, multiplied by thermal conductivity 0.02894 divided by, and its characteristic dimension is height of the cylinder. So for that purpose, height of the cylinder we have taken as in the divided to the thermal conductivity, so it is 1.5. So we'll get the value for the average heat transfer coefficient as 4.800 watt per meter square degree Celsius. Okay, now on that basis, H bar value we will get after this calculation 4.800. Now we can calculate the heat loss by the cylinder, that is nothing but Q. So heat transfer rate by convection, Q, can be written as rate of heat loss is equal to Q is equal to H bar multiplied by A suffix x multiplied by Ts minus T naught. So where this H bar is average heat transfer coefficient, A suffix s is the surface area for that particular cylinder, multiplied by in a bracket Ts is the surface temperature of the cylinder, and T naught is the fluid temperature which is flowing over the cylinder. So Q will be equal to, Q is equal to 4.80 multiplied by the surface area for the cylinder is pi dl, pi multiplied by diameter of the cylinder multiplied by its length. So pi multiplied by diameter is 0.18 multiplied by length is 1.5, and Ts is the surface temperature, 100 degrees Celsius is the surface temperature, and the fluid temperature is 20. So we'll get the Q as 325.74 watt. That will be the rate of heat loss from the cylinder. Now next problem we'll see. A sheet metal air duct carries air conditioned air at an average temperature of 10 degrees Celsius. The duct size is 320 mm by 200 mm, and the length of duct is exposed to surrounding air at 30 degrees Celsius is 15 meter long. Find the heat gain by the air in a duct. Assume 200 mm side is vertical and top surface of duct is insulated. Okay, so this is the half statement. So on that half statement we can draw the duct figure. So this is the duct, we can say that this is the rectangular duct whose cross-sectional area is 320 mm by 200 mm, and it is clearly mentioned in the problem that 200 mm side is vertical. Okay, and so that the 320 mm side will be horizontal. Now from one side of the duct the air is flowing, and from other side it is coming out. Okay, so we have to determine the loss of the heat from the, or heat gain by the duct, because the air is flowing through that particular duct at a 10 degrees Celsius. Okay, so it is also provided that the top surface of the duct is insulated. That is nothing but top surface will not transfer any heat by convection to the surrounding. Okay, so here we can say that this surface is exposed for heat transfer by convection. Now in the same manner opposite surface is also exposed for convection by heat transfer, and below surface is also exposed for convection by heat transfer, and above surface is insulated. So here we can say that the problem statement still not end over here. So problem statement is further use the following properties. Okay, the properties are given. So in that properties, the two correlations are provided. So Nusselt number is equal to 0.6 into bracket Grashoff's number multiplied by Prandtl number raised to 0.25 for vertical surface, and Nusselt number is equal to 0.27 into bracket Grashoff's number multiplied by Prandtl number raised to 0.25 for horizontal surface. So these two correlation they have provided, and we have to use these two correlation only to determine the heat gain by the duct air. Okay, and further the problem only take the properties of the air at mean temperature of 30 plus 10 divided by 2 is equal to 20 degrees Celsius as a given below. So specific heat is given as 100 joule per kg Kelvin, density as 1.204 kg per meter cube, mu, that is dynamic viscosity, is equal to 18.2 into 10 raised to minus 6 Newton second per meter square. Then kinematic viscosity is equal to 15.1 into 10 raised to minus 6 meter square per second. Then thermal conductivity K is equal to 0.256 watt per meter Kelvin, and Prandtl number is equal to 0.71. Okay, so these properties of the air at a mean temperature they have already provided, so we should not go for the table. Now the given we can write from the statement, size of duct is equal to 320 mm multiplied by 200 mm. This is the cross sectional area for the duct, and the length of the duct is provided as 15 meter long. So surface temperature of the duct will be considered as a air temperature which is flowing through that particular duct, and it is equal to 10 degrees Celsius. Then the fluid temperature which is surrounding to that particular duct, that is nothing but air temperature, is provided as a 30 degrees Celsius, and air properties at mean temperature are provided in the problem. So we have to find the heat gain by the duct air, that is nothing but Q we have to find out. Now here in the solution only we write two points related to duct. One is nothing but 200 mm side is vertical, and second is nothing but top surface of duct is insulated. So on these two statement we can imagine the diagram of the duct. Okay, so here only I have drawn this particular diagram. So 200 mm side is vertical one, okay, and top surface of the duct is insulated. So for the convection purpose we can say that this one side, that is nothing but the length of duct is 15 meter, so the area of this side will be equal to 200 mm, that is nothing but 0.2 meter multiplied by length of the duct is 15 meter. So this will be the area for this surface. Same area will be on the back side, so 15 into 0.2 meter, and the area for the lower surface, top surface, is insulated, so it will not transfer any heat, and from this side the air is taking inside that particular duct, and from other side the air coming out of the duct. So these two sides will not be considered for the convection heat transfer. So available sides for the heat transfers are nothing but vertical surfaces. Two vertical surfaces are there, and one horizontal surface is there. That is nothing but this bottom surface will be horizontal surface for the heat transfer. So we can say that, so this equation, vertical surface equation, can be applicable for the two sides, and the horizontal surface equation will be applicable for the one side. So here we have to find out the heat gain by the duct air as a Q. So we have considered the two statements. So heat loss from two vertical side having surface area 200 into 10 raised to minus 3 multiplied by 15 meter square, and one horizontal side having surface area 320 into 10 raised to minus 3 multiplied by 15 meter square, that is the length of the duct. Okay, so now we are going to consider the heat loss from the vertical surface. Okay, so for that purpose the vertical surface equation we have to use, which is provided in the problem. So vertical surface Nusselt number is equal to 0.6 multiplied by Grashoff's number, Prandtl number raised to 0.25. Okay, so here we have to find out the Nusselt number, so that we can find out the heat transfer coefficient, and on that basis we can find out the heat transfer rate for the vertical surface. So for that purpose we should know the Grashoff's number and Prandtl number values. So Grashoff's number we have to determine. So for that purpose, first of all we required the beta, that is coefficient of volumetric expansion, will be given as the reciprocal of mean film temperature in a Kelvin. So 1 divided by mean film temperature plus 273. So its unit will be Kelvin raised to -1. So mean film temperature is 20. We have determined that mean film temperature is 20. So 1 divided by 20 plus 273, and its unit will be Kelvin raised to -1. So beta is equal to 0.0034 Kelvin raised to -1. Now we can determine the Grashoff's number for the vertical surface. So Grashoff's number is equal to L cube multiplied by G multiplied by beta multiplied by delta T. So L cube is nothing but, L is nothing but characteristic dimension. So in case of vertical plates, vertical surfaces, vertical cylinders, its height should be considered as a characteristic dimension. Its height should be considered as a characteristic dimension. So in case of here the 200 mm is the height for that particular vertical surface. So height is h cube multiplied by g multiplied by beta multiplied by delta t divided by nu square. So height for the vertical surface is 0.2 and its cube multiplied by 9.81 multiplied by beta value is 0.0034, and delta T is the temperature difference between the surface and surrounding. So surface temperature is 10 degrees Celsius and surrounding temperature is 30 degrees Celsius. So we can rearrange as surrounding temperature minus surface temperature also. So 30 minus 10 divided by nu square. Nu is the kinematic viscosity. So its value is provided as given data, 15.1 into 10 raised to minus 6, and its square we have to write. Then we will get the Grashoff's number value as 2.35 into 10 raised to 7. Okay, and Prandtl number is already provided as a given data. So we can take the product of Grashoff's number and Prandtl number for the vertical surfaces is equal to 2.35 into 10 raised to 7 multiplied by 0.71 is the Prandtl number. So we will get the value 1.668 into 10 raised to 7. So we can determine the Nusselt number for the vertical surfaces. So Nusselt number for vertical surface is equal to 0.6 into bracket 1.668 into 10 raised to 7 raised to 0.25. So average Nusselt number we will get as 38.34. So Nusselt number, we know that Nusselt number is equal to heat transfer coefficient multiplied by characteristic dimension divided by K. Now in case of vertical surface, the height of that particular surface will be considered as a characteristic dimension. So H will be considered as a characteristic dimension. So HV that is nothing but heat transfer coefficient of vertical surface multiplied by height divided by K. So we can determine the heat transfer coefficient for a vertical surface by rearranging this particular equation. So heat transfer coefficient for vertical surface is equal to K divided by H multiplied by Nusselt number. So we will get the value 49.08 watt per meter square degree Celsius for the heat transfer coefficient for vertical surface. Now we have to determine the heat loss by the vertical surface or heat gain by the vertical surface. Okay, heat gain by the vertical surface. Now there are two vertical surfaces are there, so we should multiply with 2 whatever the value we are getting. So heat gain by the vertical surface can be written as 2 multiplied by heat transfer coefficient of vertical surface multiplied by surface area of the vertical surface multiplied by temperature difference between the surrounding and surface. So 2, that is nothing but 2 surfaces, vertical surfaces are there. So we have multiplied here 2 into bracket 49.08 is the heat transfer coefficient, multiply by, here the surface area for the vertical surface is nothing but its height multiply by length. So height is 0.2 meter, multiply its length is 15 meter, so 15. So 0.2 multiply by 15 will be the surface area for the vertical surface, multiply by change in temperature, or we can say that the temperature difference between the surrounding and surface. The air temperature is 30 and the duct temperature is 10. So 30 minus 10 will be the temperature difference between surrounding and surface. So we'll get the heat transfer rate, or we can say that heat gain by the vertical surface is equal to 5889.77 watt. Okay. Now in the same manner, consider heat loss from horizontal surface. So for the horizontal surface, the equation is provided in the problem. So only one horizontal surface is there. So Nusselt number for the horizontal surface is equal to 0.27 into bracket Grashoff's number multiplied by Prandtl number raised to 0.25. Now for the horizontal plate, its horizontal length will be considered as a characteristic dimension. So here we have to consider that the width of that particular duct as a characteristic dimension. So Grashoff's number for the horizontal surface will be given as L cube multiplied by G multiplied by beta multiplied by delta t divided by nu, where this L cube will be converted as a width. Okay, characteristic dimension for that particular horizontal plate will be considered as its width cube multiplied by G multiplied by beta multiplied by delta t divided by nu. So width of that particular surface, bottom surface, is 0.32 cube multiplied by 9.81 multiplied by 0.0034 multiplied by 30 minus 10 divided by nu square. Here nu square should be there. So 15.1 into 10 raised to minus 6 bracket square. So Grashoff's number for the horizontal surface we will get as a 9.58 into 10 raised to 7. Now the Prandtl number already as a given quantity. So Grashoff's number multiplied by Prandtl number will be equal to 9.58 into 10 raised to 7 multiplied by 0.71. So this product for the horizontal surface we will get as a 6.8066 into 10 raised to 7. So on that basis we can determine the Nusselt number for the horizontal surface. So Nusselt number for the horizontal surface is equal to 0.27 into bracket product of Grashoff's number and Prandtl number is 6.8066 multiplied by 10 raised to 7 bracket complete raised to 0.25. So we'll get the Nusselt number as a 24.54. So on that basis we can find the heat transfer coefficient as Nusselt number is equal to heat transfer coefficient multiplied by characteristic dimension of the surface divided by K. So in case of a horizontal plate we have to consider the width of that particular plate as a characteristic dimension. Okay, so B will be considered as a width. Okay, as 0.32 is the width. So heat transfer coefficient value if you put here, thermal conductivity value if you put here, so we can determine the heat transfer coefficient for the horizontal surface. So heat transfer coefficient for the horizontal surface is equal to 24.54 multiplied by K divided by B. B is the width, is equal to 24.54 into 0.256 divided by 0.32. So heat transfer coefficient for the horizontal surface is equal to 19.6194. Its unit will be watt per meter square degree Celsius. Now there is only one horizontal surface, so we should not multiply with another factor. In case of a vertical surface there are two vertical surface, so for that purpose we have multiplied with 2. So in case of a horizontal surface, heat gain by the duct will be written as Q suffix H is equal to heat transfer coefficient of horizontal surface multiplied by the surface area of the horizontal surface multiplied by the difference between surface temperature and surrounding temperature. So heat transfer coefficient for horizontal surface we have determined as 19.6194 multiplied by surface area for the horizontal surface is width multiplied by length. So width is 0.32 multiplied by length is 15 multiplied by temperature difference as 30 minus 10. So we'll get the QH, that is the heat transfer coefficient, heat transfer rate for a horizontal surface is equal to 1883.46 watt. So total heat gain by that particular duct or the air in the duct will be nothing but the heat gain by vertical surface and heat gain by the horizontal surface. So heat gain by vertical surface is 5889.77 plus heat gain by horizontal surface is 1883.46. So total heat gain will be 7773.23 watt. That is the second problem related to the natural convection. Okay, so next we'll move towards examples on combined free and forced convection. Okay, so we have already discussed that at very low velocity both the heat transfer phenomenon, that is forced convection heat transfer and natural convection heat transfer, plays very important role to transfer the heat from the surface to the fluid or fluid to the surface. So in that case we have to consider both the heat transfer, that is nothing but natural convection heat transfer and forced convection heat transfer. This is called as a combined free and forced convection heat transfer. So in case of natural convection, in case of forced convection, we see that the Reynold number plays very important role. As the Reynold number goes on increasing, the effectiveness of forced convection also goes on increasing. And in case of natural convection, Grashoff's numbers dealing with the effectiveness of natural convection or free convection. So by taking the average of Grashoff's number to the Reynold number square, we can analyze that which type of heat transfer, convection heat transfer, we should consider for any physical phenomena. Now here the Grashoff's number divided by a Reynold number square value, if this value is greater than 1, then we have to consider the pure free convection. So the free convection dominating over the forced convection. So maximum amount of heat is transferred because of a natural convection. So here in this case we have to consider the pure free convection. And if this value of Grashoff's number divided by Reynold number square is nearly equal to 1 or near about equal to 1, so we can say that there are both the phenomena included in that particular physical phenomena, so that we have to consider the mixed free and forced convection. Okay, that is nothing but combined free and forced convection. And if this value is less than 1, then we have to consider the pure forced convection, where this GR is nothing but Grashoff's number and RE is nothing but Reynold number. So if you are saying that both the phenomena are included in some of the cases, so in that cases we can determine the Nusselt number raised to m. The common Nusselt number we can determine, the Nusselt number raised to m is equal to Nusselt number of forced convection raised to m plus or minus Nusselt number of free convection raised to m. So this equation is used to calculate the Nusselt number for mixed convection. Now m value is equal to 3, generally recommended value. M here, the rest value is there, it is generally recommended as a 3. So now here positive, when should take the positive sign and when should take the negative sign in between this. So positive sign is taken if the free convection flow occurs in the same direction to that of forced. Okay, so both the convection will happen in a same direction only, then we can take the positive sign in between two Nusselt numbers. And if both the convection are we can say that in opposite direction, then we can take the negative sign. So negative sign is taken if the forced convection flow occurs in opposite direction to that of free convection, So some correlations are there for external flows and internal flows. External flows is nothing but flow over the vertical plate, we can say that. So in case of a flow over the vertical plates, the local Nusselt number for mixed convection on vertical plates is given as nu suffix x, that is nothing but local Nusselt number, is equal to 0.332 into bracket re suffix x raised to 1 by 2 multiplied by pr raised to 1 by 3, where this re suffix x is the local Reynold number and pr is the Prandtl number. So when we should use this relation, if the local Grashoff's number divided by local Reynold number square value is less than 1, okay, that is nothing but pure forced convection. So if you check this equation for the forced convection, same equation we will get in case of a vertical plate or horizontal plate. So in case of vertical plate only, if Grashoff's number divided by Reynold number square is greater than 1, then it will be considered as a pure natural convection or combination of natural and forced convection. Then Nusselt number, local Nusselt number will be given as 0.508 into bracket pr raised to 1 by 2 multiplied by 0.952 plus pr bracket complete raised to minus 1 by 4, where this pr is nothing but a Prandtl number. For horizontal plates, if the Grashoff's number divided by Reynold number raised to 2.5 value is less than or equal to 0.083, then will be considered as a pure forced convection. So in that case, for the horizontal plate, we can write the equation for Nusselt number. Local Nusselt number is equal to 0.332 multiplied by local Reynold number raised to 1 by 2 multiplied by Prandtl number raised to 1 by 3. Now next is, if the flow internal, in case of internal flows, we have to consider the equation. If the mixed convection in laminar flow, if there is a mixed convection, that is nothing but combination of natural and forced convection, and this convection happen in a laminar flow only, okay, then we have to use the Brown and Govin equation. So according to Brown and Govin equation, the average Nusselt number is equal to 1.75 into bracket mu suffix b divided by mu suffix s raised to 0.14 into bracket in a square bracket gz plus 0.012 into bracket gz multiplied by gr raised to 1 by 3 bracket complete raised to 4 by 3 square bracket complete raised to 1 by 3. Now here mu b is nothing but the dynamic viscosity at a bulk mean temperature, that is nothing but at a fluid temperature we have to take the dynamic viscosity, and the mu suffix s is nothing but the dynamic viscosity at the surface temperature, okay, dynamic viscosity at the surface temperature, where this gz is the Grade's number. Gz is the Grade's number. It can be given as a in this particular case, in case of natural convection, this gz can be given as a Reynold number multiplied by Prandtl number multiplied by d divided by l, that is nothing but diameter of the cylinder divided by length. This particular Grade's number should be applicable only for the circular geometries, only for the cylinders, we can say that only for the cylinders. So in case of significance of a Grade's number, we have written this, the Grade's number always used for the cylinders only, always used for the cylinders, okay. So where this gr is nothing but Grashoff's number. So this equation is called as a Brown and Govin equation in case of internal flow with laminar flow, okay. In case of a fluid, the fluid which is flowing through the cylinders, and if the flow type is laminar flow, then in that case the Brown and Govin equation should be used. Then we can say that if the flow is, or we can say that the convection is mixed convection and the flow type is a turbulent flow through horizontal tubes, then the Metides and Eckert equation should be used, and this equation is given as the average Nusselt number is equal to 4.69 Reynold number raised to 0.27, Prandtl number raised to 0.21, Grashof number raised to 0.07, multiply by d divided by L raised to 0.36. Now we'll see one problem related to this mixed convection. Here we go. A 20 degree Celsius air at 1 atmospheric pressure is forced through a 25 mm diameter tube, 400 mm long, an average velocity of 0.33 meter per second. Calculate the rate of heat transfer if the tube wall is maintained at 180 degrees Celsius. If the tube wall is maintained at 180 degrees Celsius. So given data is the air which is forced through the horizontal tube whose temperature is 20 degrees Celsius, and the tube is maintained at temperature of 180 degrees Celsius. So Ts is equal to 180 degrees Celsius. Velocity of the air is 0.33 meter per second, and the length of tube is 400 mm is equal to 0.4 meter, and the diameter of the tube is 25 mm is equal to 0.025 meter. Okay, so here we have to find the rate of heat transfer, that is nothing but Q. So solution should be start with the mean film temperature. So mean film temperature is equal to the surface temperature plus the fluid temperature divided by 2. So surface temperature is 180, fluid temperature is 20, divided by 2 is equal to 100 degrees Celsius. So we have to determine the properties of air at 100 degrees Celsius. So for that purpose, now here in the problem the properties are not provided, so we have to use the this table for the to determine the properties of air at 100 degrees Celsius. So temperature line is here. So here the temperatures are provided, and this properties of air at 1 atmospheric pressure. Okay, so 100 degrees Celsius temperature is there. So at 100 degrees Celsius mean film temperature is 100 degrees Celsius. So these properties are there at 100 degrees Celsius. So density is equal to 0.9458 kg per meter cube. Specific heat is 1009, that is 1009 joule per kg Kelvin. Then the thermal conductivity 0.03095 watt per meter Kelvin. Then the thermal diffusivity 3.243 into 10 raised to minus 5 meter square per second. Then dynamic viscosity 2.181 into 10 raised to minus 5 kg per meter second. Then kinematic viscosity 2.306 into 10 raised to minus 5, and Prandtl number is 0.7111. So these properties we have to consider to do the further calculation. So these properties we have considered over here, same properties we have considered over here. Okay, now next thing is nothing but we required the coefficient of volumetric expansion to determine the Grashof number. So coefficient of volumetric expansion, that is nothing but beta is equal to 1 divided by mean film temperature plus 273. So mean film temperature is 100. So 1 divided by 100 plus 273. So it will be 0.00268 Kelvin raised to minus 1. So this is the Kelvin raised to minus 1 is the unit for the volumetric coefficient of volumetric expansion. So we can easily determine the Grashof's number. Grashof's number. Now in case of a horizontal cylinder, the diameter of the cylinder should be considered as a characteristic dimension. In case of a horizontal cylinder, the diameter of the cylinder should be considered as a characteristic dimension. So here this characteristic dimension should be considered as a diameter of the tube. So d cube multiplied by g multiplied by beta multiplied by delta t divided by nu square will be the Grashof's number. So diameter of the tube is 0.025 bracket raised to 3 multiplied by 9.81 multiplied by coefficient of volumetric expansion is 0.00268 multiplied by temperature difference between the surface and surrounding is 180 minus 20, or the surface of tube minus fluid 180 minus 20 divided by 2.306 multiplied by 10 raised to minus 5 square. Okay, so we'll get the Grashof's number as 1.236 multiplied by 10 raised to 5. Then next thing we have to determine the Reynold number. So Reynold number is equal to velocity multiplied by characteristic dimension divided by nu, where this nu is the kinematic viscosity. So we will get velocity is 0.33 multiplied by diameter is 0.025 divided by 2.306 multiplied by 10 raised to minus 5. We will get the Reynold number 357.76. Now this Reynold number is less than 2300. Okay, so in case of tubes, if the Reynold number is less than 2300, then that flow will be considered as a laminar flow. If the Reynold number is greater than 2300, then that flow will be considered as a turbulent flow. Now here the Reynold number value is less than 2300, so we have to consider that the flow type is laminar flow. Reynold number is less than 2300, flow is laminar. Now next thing, we have to determine the ratio of Grashoff's number to the Reynold number square. So ratio of Grashoff's number to the Reynold number square is equal to Grashoff's number we have determined, its value is 1.236 multiplied by 10 raised to 5, and Reynold number is 357.76 square. So we will get the value 0.965. Now this value is near about 1. Okay, if the value is near about 1, the ratio of GR divided by Reynold number square value is near about 1, then we have to consider the mixed convection, that is nothing but combination of forced and free convection. Now in case of a cylinders, if the value is less than near about equal to 1, hence it is a case of a mixed convection. So we have to use the mixed convection laminar flow equation given by Brown and Govin. So Brown and Govin given the equation, average nozzle number is equal to 1.75 into bracket mu suffix b divided by mu suffix s into square bracket gz plus 0.012 into bracket gz multiplied by gr raised to 1 by 3 bracket complete 4 by 3 raised to 4 by 3 square bracket complete raised to 1 by 3. Now this mu b is nothing but dynamic viscosity at bulk fluid temperature. Okay, mean bulk fluid temperature. So bulk here the average temperature of a fluid is provided as a 20 degrees Celsius itself, and that value we have to determine 20 degrees Celsius. Now here the 20 degrees Celsius is there, so at that temperature the dynamic viscosity value is here. Dynamic viscosity value is 1.825 into 10 raised to minus 5. Okay, so that value only we have taken over here, 1.825 into 10 raised to minus 5 kg per meter second. So next is mu suffix s, that is nothing but dynamic viscosity at the surface temperature. So surface temperature is 180 degrees Celsius. So we have to check this value for the dynamic viscosity at a surface temperature. So surface 180 degrees Celsius. So 180 degrees Celsius value for the dynamic viscosity is 2.504 into 10 raised to minus 5. So this value we have to consider over here. So mu suffix s at 180 degrees Celsius is equal to 2.504 into 10 raised to minus 5. Then we have to find out the Gray's number. So Gray's number will be written as, in this particular case, Gray's number is written as a Reynold number multiplied by Prandtl number multiplied by d divided by L. So d is the diameter of the cylinder, L is the length of the cylinder. So Gray's number will be, we will get Reynold number already we have calculated, it is 357.76 multiplied by Prandtl number we have taken from the property table 0.7111 multiplied by diameter is 0.025 and the length of the tube is 0.4. So Gray's number we will get as 15.90. Now we have to consider the Brown and Govin equation. Okay, and this nozzle number will be equal to 1.57 mu b divided by mu s bracket raised to 0.14 in the bracket Gray's number plus 0.012 in a bracket Gray's number multiplied by Grashoff's number raised to 1 by 3 bracket complete raised to 4 by 3 square bracket complete raised to 1 by 3. Now we have to put up all these particular values in the nozzle number equation. So average nozzle number is equal to 1.75 into bracket mu suffix b value is 1.825 into 10 raised to minus 5, and mu suffix s value is 2.504 into 10 raised to minus 5. So Gray's number we have calculated as 15.90 plus 0.013 into bracket, once again Gray's number as 15.90 in a bracket 1.236 into 10 raised to 5 is the Grashoff's number value. The Grashoff's number raised to 1 by 3, curly bracket complete raised to 4 by 3, and square bracket raised to 1 by 3. Okay, so we'll get 1.75 multiplied by 0.9566 into bracket 15.90 plus 0.012 in a curly bracket 792.020, curly bracket complete raised to 4 by 3, square bracket complete raised to 1 by 3. So nozzle number equal to 1.67 into bracket 4.7001. So nozzle number, average nozzle number value you will get as a 7.84. So we know that nozzle number is equal to HD divided by K. So H bar is nothing but the average heat transfer coefficient. D is the diameter of the cylinder, as we are considering it as a characteristic dimension for the cylinder. K is the thermal conductivity. So nozzle number is known, D, that is the diameter of the tube, is known, then thermal conductivity is known. We can easily find out this average heat transfer coefficient. So average heat transfer coefficient is equal to average nozzle number multiplied by thermal conductivity divided by diameter of the tube is equal to 7.84 multiplied by 0.03095 divided by 0.025. So we'll get the average heat transfer coefficient is equal to 9.717 watt per meter square degree Celsius. Now on that basis we can determine the heat loss or heat gain by the cylinder. So Q is equal to H bar multiplied by A suffix S multiplied by delta T. So H bar is heat transfer coefficient, A suffix S is the surface area for the tube or the cylinder, and delta T is the temperature difference between the fluid and the cylinder surface. So H bar value we know that we have calculated. So 9.717 multiplied by surface area for the cylinder, we know that pi dl. So d is the diameter, l is the length of the cylinder. So pi multiplied by diameter is 0.025 multiplied by length is 0.4 multiplied by temperature difference between the surface of the cylinder and the fluid flowing through it, that is nothing but 180 minus 20. So the heat loss by the cylinder will be Q is equal to 48.84. Thank you.